Happy for the invitation. Yeah, so today I'll be talking about gravitational waves. So I'm a physicist, so we'll start with a brief introduction about what gravitational waves are and about gravitational wave astronomy and physics, and the challenges that we face now and that we will be facing in the next decade or so. But because I've been told that we're not all physicists here, I will not dwell on physics very much, aside from a very fast introduction. But I will also delve into the machine learning applications to gravitational wave astronomy. And this is the choice of topics is personally biased because it's based on what I did. Yeah, sorry. Can you guys hear me online? Yeah, sorry, I didn't. I tend to walk very much when I give presentations. So in the second part of the talk, I will present a few applications of machine learning to gravitational wave astronomy, which is, I understand, something that is the focus of this crowd. And in particular, I will be talking about black hole ringdown and Lisa galactic binaries. Again, this is a choice dictated by personal bias, but at least you get a feeling of what is the power of these techniques in gravitational wave astronomy. I should mention that this is not work I've been doing on my own. This has been done and is being done with collaborators at CISA that range from data scientists like Roberto Trotta, gravitational wave data analysts or gravitational wave physicists like Chantal and Lorenzo, machine learning persons like Raul, and collaborators also elsewhere like Marco and Callot. So without further ado, what are gravitational waves? I guess if you're a physicist, you know that they were predicted by Einstein about a century ago, more than a century ago, and they're essentially tidal forces. Really, gravitational waves are produced by moving masses traveling at speeds close to the speed of light, so they're not important on Earth because we don't have very large masses and very large speeds on Earth. But they're very important in astrophysical settings, binaries, such as those that Emilio mentioned, black holes and binaries of black holes and neutron stars. They carry energy of momentum, which is something that was not really understood until finally until the 70s, not the last centuries. And they can be thought really as tidal forces. So if you have a ring of particles, and if you consider a gravitational wave orthogonal to the slide, the ring of particles will be deformed in a quadrupolar fashion by a passing gravitational wave. And this is the detection principle that we employ to observe gravitational waves. So we use interferometers, laser interferometers, and gravitational waves modify the distance between the mirrors of the laser interferometer. And by computing the phase difference between the lasers at a common collection point, you can try to detect these tidal forces. So what you measure is really what we call, in jargon, the strain exerted by gravitational waves on the arms of the detector. So in the remainder of the talk, when I'll be talking about strain, I really mean the signal. This is a very difficult measurement because the strains that we're considering, the deformations of the arms, are of the order of 10 to the minus 18 meters, which is less than the size of a proton. So it's a very challenging measurement from an experimental point of view. And so for this reason, it's a very noisy measurement. There are lots of sources of errors in this measurement, which in the remainder of the talk, I will refer to as noise. And this is a central thing that we will need in the following. So we had a strain, which is our signal, plus the instrumental noise, which can be caused by anything from the laser quantum noise, the laser shock noise, the thermal excitations of the mirrors, the suspensions that keep the mirrors attached to the ground, and so on and so forth. So as you might have heard, even if you're not a physicist, we did detect these gravitational waves about a century after Einstein predicted them in 2015. This was the first signal of gravitational waves that we ever observed. So this is again the strain, the relative change in the distance between the two mirrors of a detector. And you can see that it has this peculiar shape, what we call a chirp. So the frequency of the signal increases. The raw output of the detector is the top panel. And you see there are these spikes, which are what we call the instrumental noise. So the signal here has been already cleaned. We applied pass filter, but still you can see residual noise, which we would like to eliminate. So this is the merger. So this signal results from the merger of two binary, of two black holes of 30 and 35 solar masses. So the plot here shows the same signal in the time frequency space. So essentially you apply a Fourier transform to the signal as function of time. So you take a first chunk of the signal, you take a Fourier transform, and you plot the power in the color code. And you see that the power is distributed mainly on this banana-shaped curve, which we can predict with general relativity. So this is a validation of Einstein's predictions about a century after these gravitational waves were first predicted. This is, by the way, the signal as it would look like if you could subtract the noise. So there are techniques whereby you can subtract the noise, and this is the cleaned up signal. However, the first detection this was the detection by the American detector LIGO. There is also a detector in Italy, Virgo, which is also participating in the experimental effort, just happened not to be on at this time. This was only the beginning. Since 2015, we observed almost 100 of these systems with a variety of masses and natures. So in blue here, we represented graphically the binary black hole mergers observed by LIGO and Virgo and Kagra, which is a Japanese detector. So the two dots are, the size of the dots is proportional to the mass of the black hole. So you see here two black holes that merge into a bigger one. The mass is also shown in the vertical axis. So you see we've observed a lot of binary black holes, handful of binary neutron stars, only one of which, however, we saw also in the electromagnetic band. And also shown here are systems of black holes and neutron stars that we observed in the electromagnetic band. So they cover a slightly different region in parameter space, which is astrophysically interesting. So typically the black holes that we see in gravitational waves, for some reason, are bigger than those that we see in the electromagnetic, which is something that we still do not understand. This, however, is also just the beginning of our journey to observe the universe through gravitational waves. There are even bigger black holes than those that we observe in LIGO and Virgo. So we have a black hole of about more than 1 million solar masses in the center of our own galaxy. So for the non-physicists, we really do observe a mass, a dark mass in the center of our galaxy, and we see its dynamical effect on stars orbiting it. So we can just use Kepler's law to measure this mass, and it turns out to be 4.5 million solar masses, which is within our current understanding of physics, cannot be supported by anything but a black hole. So in these black holes, which are 1 million times larger than those that we observe today, also merge, because in our current understanding of galaxy formation, galaxies merge. So if each of these monster black holes is located in the center of a galaxy, because galaxies do merge hierarchically in the lambda CDM model, the black holes contained in them will also merge. In fact, there is a famous, okay, I'm not sure if I should go into the details given this crowd, but there is a famous relation between the mass of the black hole contained in the galaxy and the velocity dispersion of the stellar population, which is still one of the mysteries in astrophysics. And this is the kind of physics that we will be able to explore with if we observe the mergers of these supermassive black holes. In fact, maybe I'll skip this slide. So just to make a long story short and look at the future. So we're now in 2025. We've observed about 100 gravitational wave events. And these signals are relatively loud. So the ratio between the, if you want, the strain that I mentioned in the beginning and the noise of the detector is of the order of 100. So if you want, the signal is 100 times louder than the noise in some sense, which I can clarify. This is where we stand now. This is where we stood in 2015, where we had just a handful of detections. So thanks, and this 01, 02, 03, or 04, 05 are essentially different stages, experimental stages of the detectors that we have today, LIGO, Virgo, and Kagra in Japan. So they're American, European, and Japanese detectors. However, in the next 10/15 years, we have a plethora of new detectors, both on the ground and in space. So this A hash is simply the next, well, it's simply an update to current detectors, but in the beginning of the next decade, we will have next generation detectors on the ground, Einstein telescope in Europe, Cosmic Explorer in the US, and most of all, space-based detectors like LISA, which will enhance the number of sources that we will detect up to millions. So we'll detect up to 10 to the 6 sources with signal-to-noise ratios up to 10,000. So there will be much louder signals and many more. And this poses a problem from the data analysis point of view, which we can try to tackle with classical techniques, Bayesian techniques, but where I think also machine learning could provide a significant opportunity. So what is the problem? The problem is that if we have very loud signals, we will need to interpret these signals also very accurate predictions from theory. So the way we work in gravitational wave physics, we have exquisite physical predictions for our signals, and we use these predictions to infer physics from this data. And this physics ranges from astrophysics to fundamental physics to cosmology, and perhaps also more exotical, unexpected discoveries. And there's a lot of activity, and each of these topics would require a talk in its own. So, and because we're not all physicists here, I will not dwell on this, even though I'm happy to answer any questions. But to extract physics from the data, we need very good predictions from theory. And today, we don't have these predictions in the sense that our predictions are affected by what we call systematics. So we cannot solve the Einstein equations to the precision needed to extract physics from the data. I will show in the next slide what I mean by this. Also, we don't understand our noise sufficiently well. I mentioned at the beginning that this is a very challenging measurement from the experimental point of view, because we're measuring things which are very small, less than the size of a proton. So we need to understand the noise, so the experimental noise. We need to understand our detector. And we typically model this noise as a Gaussian stationary process, which is definitely not the case in real life. And this is, again, where machine learning could help. We will have many sources superimposed one with another, because we'll have so many sources that they will overlap. So there could be biases in our reconstruction of the physics due to the fact that we have overlapping sources. There could be influences from the astrophysical environment, which we do not account. Currently, our predictions assume pure vacuum. So we need to understand these astrophysical foregrounds, even though there are So what do I mean by waveform systematics, and what do I mean by theoretical predictions? So we have many sources of gravitational waves that we expect there to be in the data, which range from black hole binary mergers to what we call extreme mass ratio spirals, which are made by a big black hole and a small black hole. Galactic binaries, which are white dwarf binaries, stochastic gravitational wave backgrounds, maybe more exotic sources like cosmic strings. So you don't need to understand all this, but you should understand that in our data, we will have different family of sources, each of them with a different time series. This is a cartoon representation of the time series that we expect for each of these sources. And we have predictions for each of these time series, but these predictions come from solving the Einstein's equations of general relativity under some approximations. Post-Newtonian theory, gravitational self-force approximation, numerical relativity, which all have a different range of validity. So these predictions have systematic uncertainties due to the fact that we cannot solve exactly the theory describing the gravitational interaction in nature, namely general relativity, even in vacuum. So these waveforms, as we call them, these predictions are accurate enough for current detectors. They will not be necessarily accurate enough for future detectors. So this is something that we need to account for. I mentioned that we could have many sources superimposed one with another. This is an example of what the data will look like with LISA, which is a detector in the millihertz, which will fly in 2035, and for which we're developing data analysis techniques now. So there will be tenths or thousands or more sources superimposed in the data. This is the Fourier transform of simulated data for LISA. And you see here lots of spikes. Each of these is a monochromatic source, one of these galactic binary sources. And we need to extract all of them. So we expect that there will be at least 10,000 such sources in the data, which we need to extract. There will be signals due to EMRIs, which will be these time series, which here in the frequency domain, they give rise to these to this signal. Each color, which you can probably barely see, is a different source. We will have supermassive black hole binaries. We will have stochastic background, and everything will be there together. So it becomes a separation problem. So we need to separate all these components in the data. And if you think of it as an inference problem, if you want an optimization problem in several thousands of dimensions, because each of these sources has its own parameters. Each source has, on average, 15 parameters. So 15 times 10,000 is more than 10 to the 4 parameters. So we need to find if you want the maximum of, if you want the likelihood or the posterior or your loss function in tens of thousands of dimensions. So this is a problem which in full generality is not yet solved. Also because we don't know how many sources there will be in the data, and how many sources there will be for each class. This is what we expect, but nature could surprise us. And so far, it's always surprised us when we looked at different frequencies in the sky, even in the electromagnetic band. So this is one of the biggest problems that we have today in the field from the data analysis point of view. So essentially, just to summarize, what we will have will be data with many sources superimposed. We'll have theoretical predictions on this side, and essentially using these data, which I refer to here, using this data, which I call S, which are given by the strain, the real signal, plus the instrumental noise. We want to reconstruct the parameters theta of all these sources in order to extract physics. And in principle, this is something, if you have your favorite Bayesian sampler, you can we know how to write the likelihood under some assumptions on the noise, and you can try to get posteriors for your parameters. But in practice, because you have so many sources on at the same time, this becomes a very challenging problem. So here, I show some posteriors for the masses of the supermassive black hole binaries and their spins produced by different groups for the same simulated data set. And as you can see, they roughly agree, but not always. And this is only for the loudest sources. So this separation problem is definitely, which we call the global fit, is not yet solved. In fact, what we think we will do is to tackle the problem in a iterative way. So we'll subtract the loudest sources first, and then so we start from the loudest sources, the massive black hole binaries. Well, in fact, no, sorry. So we'll first start probably from the galactic, massive black hole binaries, and then we'll probably go on to the galactic binaries and subtract them one by one. And this is not clearly the correct way to proceed, because in principle, you should fit all sources at once. But we'll probably proceed in an iterative way and check to get at least the first idea of the parameters of each source, and then try to find the solution to the global fit. So this iterative, what we call the global fit wheel, of course, has several problems, because the noise, because the sources which you don't subtract contribute to the noise. So the noise needs also to be a free parameter. So the noise needs to be estimated too. And there are also probably competing maxima that can be present. So degeneracy between the different classes of sources. And of course, if you don't subtract a source correctly, it leaves a residual power in the data, and this whole iterative procedure can fail. So this is how we think we will tackle this problem within a classical Bayesian settings. Well, this is not fully Bayesian, but this is the closest we can get given our current technology. So how can machine learning help? This is where I'm going out of my comfort zone, because I'm not, as I said, I'm a physicist, and I got real interested lately in machine learning exactly for this global fit problem. So can machine learning help for the global fit? Well, one way in which machine learning can definitely help is in our characterization of the noise. Because when we do this, sorry for going back and forth. When we do this Bayesian analysis, we need to write a likelihood, right? The probability of the data given the parameters. And there we can write this likelihood analytically if we assume that the noise n is Gaussian and stationary, which is typically a good approximation on short time scales, but definitely even for LIGO and Virgo, it's not always a good approximation. The noise level can fluctuate. There can be glitches in the data. There can be a thunderstorm hitting the detector, and that chunk of noise you have to eliminate and cannot use it. So this is a key approximation how we do the data analysis. And this is an assumption which can be bypassed if you use techniques like simulation-based inference. In fact, if you could, if you can just simulate the noise, or maybe extract chunks of the noise from your data in regions where you don't expect there to be any sources, you could actually use these forward simulations of the noise to invert to derive posteriors from the data, which do not assume Gaussian and stationary noise. So how do you do this? So what you would like to find is a representation of the posteriors. So the posteriors of the probability of the parameters given the data. And you can represent this, this posterior with a neural network, or as I will explain in the next slide, with a normalizing flow, or some expressive parameterization of these posteriors. And what you can do, you can try to minimize the expectation, the distance, if you want, between this representation and the true posteriors. So you can write your loss as the expectation over all possible realizations of the data of the distance, meaning the cross entropy between the posteriors, the true posterior and the representation. So the cross entropy it's the expectation value over the true posterior of the log of the representation of the posteriors. And then you take another expectation value. You want this to be on average correct, so you take another expectation value over all possible realizations of the data. And so this would be your loss, except that, of course, you don't know your posteriors. So what you can do is to, because you cannot run, you don't want to run an MCMC or next sampling to get the posteriors and write your loss. That would be the purpose of having a machine learning simulation-based inference pipeline. So what you can do is to use Bayes' theorem to invert the order. So write this P of S times P of theta conditional S as, you see, the expectation over the prior time expectation over the likelihood of minus the log of the representation of the posteriors. And so what this means, if you think about it, is that you can write your loss function as the average over the average of the log of this neural network, which is to represent the posteriors, over all possible realizations of the data obtained with parameters sampled from the prior. So essentially, you can do forward simulations for parameters that you randomly sample from the prior. You do simulations of the data, given those priors, and you compute Q of theta I Si, and then you take an average over many of these simulations. So in order to write this loss, you just need simulations. And then you can minimize your loss function in the usual way. And so what remains to find is a representation of the posteriors, which is sufficiently expressive. So what we try to do in the examples that I will be showing shortly is to represent these posteriors with normalizing flows. So what normalizing flows are essentially a transformation of a complex distribution, which is our posteriors, which are multimodal, highly dimensional, into a latent space distribution, which is very simple. So in this case, we choose a normal distribution normalized to 1. And these normalizing flows, you can parameterize with neural networks. So here we use masked autoregressive flows or splines. So, but from the analytical point of view, normalizing flow simply maps a latent space distribution, which is very simple, a Gaussian, into a very generic distribution in real space. Of course, this distribution depends on the weights of the neural network, and this is what we will minimize our loss. So to summarize, what are the advantages of such a parameter estimation or inference approach? Well, this is a very general technique. It can handle very complex likelihoods, likelihoods which are not tractable analytically. And this is, in fact, a key advantage for us because we don't need to assume stationarity or non-Gaussianity in the noise. We don't need to assume stationarity or Gaussianity for our noise. So we can just take chunks of the noise in regions of the data where we expect there to be no signal and use those to simulate the noise and make no assumptions on the statistics of the noise. Once trained, this posterior evaluation is fast, so it's amortized, so we can get the posteriors in real time, as opposed to running MCMC or nested sampling, which can take days, if not weeks. And also because we can evaluate the posteriors very fast, we can actually check the results of our inference and produce PP plots, coverage plots, so we can check if our posteriors have the right size. If the 1 sigma, for instance, intervals of our posteriors really contain 65% of, contain the ground truth 65% of the time. And if they're not, if the posteriors are not, don't have the right coverage, we can also correct. So I'm already halfway through my talk, so maybe let me show you an application. So this is a very simple application. So I'm still considering ground-based detectors. And I'm considering what we call the ringdown phase of a black hole merge. So this is the same signal that I showed you on slide 1. So the early part corresponding to the inspiral phase in which we have 2 black holes orbiting with one another. At some point, the 2 black holes merge. And the post-merger part is this dense sinusoid part, which we call the ringdown. So we have very good analytic models for this ringdown part. And this model it's essentially a superposition of damped sinusoids. So there's nothing fancy about it. So it's simply here in complex notation, sines and cosines with exponentially damped amplitude. And the parameters of these damped sinusoids, the frequency and the damping factor, are frequencies of the physical parameters of the system, the mass and spin of the black hole. So this is a key prediction of GR, that there are only two parameters in these frequencies and damping factors. Even though there can be many sinusoids, the frequencies and damping times of all these sinusoids need to be function of just two quantities, mass and spin. And this is what we call the Noether theorem of general relativity. Whereas the amplitudes and the number of modes that we have in the data are essentially free parameters, as they depend on the prior history of the binary. So this is, in fact, I mean, these sources are very important as they allow us to test the predictions of GR, in particular the fact that these complex frequencies depend only on the mass and spin. So, and this is not just a problem of academic interest. For the first source of gravitational waves that humankind observed in history, there is still debate as to what are the properties of this ringdown. These are two very influential papers that appear in the last few years by a group at MIT and Cornell, a group at JHU, Johns Hopkins University, where they find conflicting evidence for the presence of, for the number of modes that appear in this summation. So one paper suggests that there is only one mode in this summation. The other paper suggests that there are two modes. And they don't agree. They tackle this problem with classical Bayesian techniques, different samplers, they get different results. So we thought, okay, why not try to use simulation-based inference, because it would allow us to check also the assumption of Gaussian stationary noise, which these papers conjectured could be the reason of the disagreement between them. So these papers, they don't agree, and they say maybe one of the problems is that we assume Gaussian stationary noise, which is needed to write a likelihood. So what we did, we trained a simulation-based inference pipeline with real noise and with Gaussian noise. So essentially, we do forward simulations of the ringdown signal for 150914, which is the first event, with Gaussian noise and with real noise. And we try to obtain the posteriors for an injection, meaning simulated data with real noise. So this real noise injection is not assuming Gaussian noise, and we try to analyze this data, assuming Gaussian noise or using the same results, or using the same statistics as in the simulation. So essentially, these are the blue and the green curves. So if the noise in the data were to be non-Gaussian, the blue and the green would have to differ. And as you can see, these are different parameters, the mass, spin, the amplitude of the two modes that we think could be in the data, the 220 mode, the 221 mode, their phases. And as you can see, the posteriors for the blue and the green essentially coincide. So this tells us that the noise around 150914, the first gravitational wave event, is to good approximation Gaussian. But still we see that there is a difference with what we obtain with PyRing, which is the official Bayesian sampler of the LIGO-Virgo collaboration. So the posteriors are somewhat different, especially if you look at the 2D scatter plots. So what we did, so this means that even though this simulation-based inference pipeline seems to work, probably the posteriors that we get are not, are probably, as you can see, too large. They're too large than the Bayesian posteriors. So what we did was indeed to check this assumption. So we checked, if you're familiar with the concept of PP plots, we produced a two-dimensional PP plot, or as we call it, a coverage plot. So we checked because now inference with normalizing flows is very fast. So we could produce many simulations, we could inject many simulated signals in the noise and try to extract them, obtain posteriors for each one of them, and try to understand and try to count how many times the ground truth was within the, I don't know, the 1 sigma or 65% confidence region. And because this actually allows us to check if our posteriors are faithful or not, are good or not. This is not something that you can do with traditional Bayesian techniques, because to run an inference with Bayesian techniques takes days. And in fact, what we found is that our pipeline in some regions of the parameter space is too conservative, so our posteriors are too large. In some other regions of parameter space, it's undercovering, so it's the posteriors are too small. And this has implications in particular for the question of whether we have one mode or two modes. These are the amplitudes of the two modes, the 2-2-0 and 2-2-1 mode. And the posteriors that we get with our normalizing flows are given by the orange and yellow regions. I think these are 60 and 90% confidence regions. Sorry, the uncalibrated, yeah, so it's the black. So what we get with our original pipeline is the black lines, but then we can correct for this under or over covering of our posterior. So we can, because we know where our network fails, and we can correct for that. And if so, we get posteriors, which are in orange, which are in much better agreement with the Bayesian posterior. So this is a good thing about SBI, simulation-based inference, that it allows you to check the goodness of the posteriors, and if the posteriors are not good, you can correct them. Another way in which you can correct these posteriors is if you have a likelihood available, you can actually do importance sampling, so you can get samples from your neural network posteriors and correct them, and evaluate the likelihood for each one of those samples, and correct the posterior samples that you get with a weight which is proportional to the likelihood times the priors, which you can evaluate over the posterior. So you can do importance sampling to correct your posteriors. And if you do so, you can see it here. I don't have time to enter into too much on this. The posteriors that you get for 150914 with SBI are essentially spot on with the Bayesian posteriors. And in particular, if you look at the posteriors for this is the physical question we want to answer, the posterior for the mode that we don't know whether it's in the data or not, the 2-to-1 mode, we will find that the posteriors there is mild evidence for this extra mode, but not very much, as you can see. The posteriors are well compatible with 0. One more thing that you can do for free once you have such a normalizing flow pipeline is also to estimate the evidence. So estimating the evidence is typically hard if you have Markov chain Monte Carlo techniques. And the golden standard is to use nested sampling. If you go through the math of how normalizing flows are constructed, normalizing flows they map the original posterior into a Gaussian in Latin space, which is normalized 1. So essentially all the information of the integral of the posteriors, which is the integral of the likelihood times the prior, is encoded in the Jacobian of the normalizing flow. So essentially, I mean, I can go through the math here. If you can evaluate the likelihood for each of your posterior samples, you can take the likelihood multiplied by the prior, divided by the posteriors produced by normalizing flows, and you get for free an estimation of the evidence. So this is something we also looked at. So we have a free publicly available code that does this. So if you provide samples with likelihood values for each sample, we can compute the evidence, which is crucial when you want to compare models with one another. So we tested this on a number of analytic likelihoods, Gaussian, Rosenberg, exponential, mixture of Gaussians, up to 200 dimensions. And it works very well, even when compared to the golden standard, which is nested sampling. I don't want to spend too much time on this because I'm been speaking for about 40 minutes now. So what we did was now to apply this evidence estimation technique to 150914, to the ringdown, because we wanted to compute the base factor in favor of the presence of one mode over the presence of two modes in the data. So, and here again, we compared our results with what we get by nested sample. ZNS is the evidence as estimated by nested sample. Yeah, but so, and our estimation agrees very well with nested flows. Is our estimate with normalizing flows. The psi here is the nested sampling estimate. And you can see the log of the ratio of the two is essentially 0. So there is a good agreement. And when we go about computing the base factor for the physical problem at hand, so base factor in favor of having two modes over having one mode, nested sampling and our normalizing flow pipeline, they agree. They agree that the base factor is very close to 1. So there is no real evidence of additional modes in the ring down of the first gravitational wave event. For comparison, we also try to compute the evidence with the nearest neighbor technique, which is available, was described in the literature. And interestingly, this technique gives a different result. So if you want, not only so our technique using normalizing flows is comparable to the golden standard nested sampling, unlike other techniques available in the literature. So we did this for the first gravitational wave event. We also went about looking at other gravitational wave events. There was a particularly interesting event in the community, which was 190521. This phone number means that this was detected on the 21st of May, 2019. So this was the biggest black hole observed by humankind so far. So the biggest black hole merger. So the masses are very large for us, for our understanding of stellar evolution, 85 and 66 solar masses. And here again, there were claims that the ring down from this particular black hole event may have two modes, not only one damped sinusoid, but two damped sinusoids. And so we tried to apply the same technique to this event. The difficulty with this event is that it's really very short because it's very massive. So it essentially glitch. This is in time frequency space. So it's a very short event. You essentially only see the ring down because of the high mass and the properties of the instrument. So these are LIGO, Virgo, the two LIGOs and Virgo. Virgo doesn't see anything because it's in a blind spot because of the sky position. So we try to do the same. And again, we find that the noise around this event is very Gaussian. So here again, these are the SBI simulation-based inference or normalizing flows posteriors obtained assuming Gaussian noise, obtained without assuming Gaussian noise, and the posteriors obtained with a Bayesian sample. I think it's PTMC. And as you can see, in some cases, SBI actually produces contours which are actually better than even the Bayesian sampler. The Bayesian sampler producing this island, which I don't think is physical. But by and large, the posteriors are in good agreement with the Bayesian samplers. which assume Gaussian noise. So again, there is no evidence yet of non-Gaussianities or non-stationarities for this particular event, but this is simply due to the fact that this event is very short. So it's very hard to, if there are non-Gaussian tails in the noise for this event, because the event is so short, it's very hard to see the effect in such a short event. But again, in principle, SBI can do without any assumptions on the noise. Do I have 5 more minutes? Yeah, this is what we've been doing so far using the ringdown. I want to say more about the global fit. This is work in progress, and I don't have much time to go through the details. But we're also trying to use this, this technique to tackle the LISA global fit. So this problem, in this optimization problem, is in tens of thousands of dimensions that I mentioned at the beginning, which we plan to, we have no choice, perhaps, but to treat in an iterative way by subtracting the sources one by one. One of the things with this wheel, with this iterative procedure, is that it's very costly. So because you need to subtract tens of thousands of sources, even if you do it a source one by one, your inference needs to be very fast. You cannot possibly wait days to subtract the source because you have tens of thousands more sources. So the idea that we're pursuing, which is still preliminary, is to try to use simulation-based and amortized simulation-based inference pipeline, if you want, to tackle this problem. So this is what we're trying to do. We're tackling first the case of galactic binaries. So these sources, these blue sources, which count in the number of tens of thousands, they're very simple sources, monochromatic, but you can't just take a Fourier transform because there are so many of them that it's very hard even to take a Fourier transform because it's a very long signal. So what we're trying to do is to subtract each of these sources one by one. So we're trying to train a normalizing flow to detect one of these sources. So this is the problem that we're trying to solve. So these are the parameters of just one of these galactic binaries. And these are the posteriors as obtained with SBI and PTMC, which is essentially parallel tempering Markov chain Monte Carlo. And yeah, the posteriors are somewhat similar. For some parameters, our SBI pipeline still doesn't just reproduce the priors. You see these horizontal lines means that the SBI doesn't manage to find the true posteriors. But these are encouraging results. And for instance, for some parameters like the frequencies, so these are the two-dimensional marginalized posteriors for the frequencies, and we can extract them very easily with SBI. So the idea is to use this amortized pipeline to do this iterative procedure and subtract iteratively each of these tens of thousands of sources. And again, the key thing is that this SBI is amortized, so you don't need to train it every time. I think I'm going to stop here. We also have ideas on how to do hierarchical Bayesian inference for the astrophysics using SBI, but this is also still quite preliminary. So maybe I'll stop here. Let me try to summarize what I've been trying to convey in this talk. So in the next decade or even earlier, with updates to current facilities, we are guaranteed to see anomalies in our gravitational wave data. Because what do I mean by anomalies? Deviations from our predictions, from our GR, general relativity vacuum predictions for gravitational waves. And we need to disentangle, we need to understand the origin. We will need to understand the origin of these deviations. Some deviations are expected. The astrophysical environment Others, or waveform systematics, we know our models are not good enough for future detectors. So we're working to model both waveform systematics and the astrophysical environment. But some other possible origins of anomalies are due to the data analysis and the properties of the noise. And those can be tackled with normalizing flows, simulation-based inference, perhaps other machine learning techniques. Why do we want to do this? Because really, when we do physics, we want to test our physical theory. So our physical theory of choice for gravity is general relativity. So the holy grail for our field is to see possible deviations from general relativity. But if we cannot subtract all other systematics due to the environment, due to approximation that we make when solving for the waveforms, due to the data analysis, we'll never be able to test general relativity. So some advantages of machine learning, I use this word in general sense, although here I focused on normalizing flows and simulation-based inference, is that it provides potentially fast / amortized data analysis techniques. So because we will have so many sources in the data, we cannot take days to analyze each one of them. So this is definitely an advantage. The other advantage is that we can handle non-Gaussianities or non-stationarities in the noise, which will be much more important with future detectors than today because the signals will be louder. And so biases will become statistically significant. We can easily check if the posteriors coming from machine learning are correct. So we can compute PP plots or coverages easily, essentially because our inference is very fast. Okay, and this point may perform population inference directly. I didn't cover, so forget about it. Cons are that sometimes, at least in our naive usage of SBI or normalizing flows, we don't really get very faithful posteriors, so we need to correct. So the coverage is not really what we would like, and so we have to correct these posteriors. So we would like to improve that part. But again, we're physicists and not computer scientists, so we're struggling to do that. So so far, what we're doing is to do important sampling with the likelihood to correct our posteriors, which is still more efficient than running fully Bayesian inference, but it's not optimal. And the other con is that still, even though you train only once, you need millions or more simulations to train these machines, and this is expensive. So it's as expensive as calling the likelihood. So we're not in a case. So the complications in the cost in our inference doesn't come from the likelihood, which is very simple, but really comes from our theoretical model. So slow training is the other drawback of these techniques. Yeah, I think this exhausts what I wanted to say today. Again, this is a physics viewpoint. I'm happy to discuss more about the physics, or if you have suggestions on the machine learning part. Yeah, thank you for your attention. I'm happy to take any questions.
Hello, thank you, Enrico, for the nice talk. Is there any question? Yeah, also for Zoom, from Zoom, if you want to ask questions.
Yeah, so thank you for the talk. I wanted to ask a question about this last point about the disadvantages here, so that you have to weigh your posteriors with, for example, a likelihood. So in terms of the LISA data you will get, I mean, the likelihood will be extremely complex. So is this any, viable way to go forward if you want to tackle that type of data?
Yeah, that's why I'm saying that this result is still preliminary, because yeah, we would like to get much better agreement with Bayesian than, I mean, it's still better than doing pure Bayesian because you essentially use your SPI posteriors as proposal for your MCMC. So it's still better than nothing, but still, it's the acceptance ratio here is not very high. So this weight, when you reweight by the likelihood, this weight can be very small. So essentially, what we're trying to do here for the moment is to use SBI. So one parameter for which we get very good posteriors are the frequencies. So we're first doing the first pass. So essentially, we break up the data in chunks. So we have, these sources are quasi-monochromatic. So we break them in chunks of about 100 frequencies, where we expect there to be about 10 sources. We run the SBI on these 128 frequencies that we have. And the posteriors that with SPI, that we trust with SPI are the posteriors for the frequency. And because you see these different islands, here there were two sources and we can see two different blobs. So we use SPI to count how many sources there are in the data, because we don't know how many sources there are in the data. So we use SPI to count how many sources there are in the data, and then we run PTMC with 10 sources or 2 sources or whatever. So this is what we're doing so far, but it's not optimal. Yeah, this is where I would like to improve.
Okay.
But we don't know how, because it's even for the ringdown, it doesn't work perfectly well. This was the, even here, it's not, the posteriors are not exactly the same.
Right. And for now, you're doing only neural posterior estimation, but
Yes.
have you experience also with neural likelihood estimation or neural ratio estimation for this type of analysis?
Say again, sorry.
And do you also have experience in your group
No.
with neural ratio or neural likelihood estimation for this
I
type
think
of?
Roberto Trotta has, but we haven't tried.
Okay.
On the to-do list. I don't have hands-on experience.
Okay.
But I'd be interested if you have suggestions of what we.
There is a question from remote. If you want, you can speak loudly.
Yeah, am I audible?
Where does it go here? Okay. Okay.
Yeah, you can speak.
Please go ahead.
Right.
Okay, can you listen me?
We can hear you, yes.
Okay, my question is that can we use the signal to noise ratio as a suitable criteria for non-Gaussian noises? Because as I believe that these non-Gaussian noises, the first and second order moments does not exist. So how can you use this criteria SNR for these non-Gaussian?
I think, I'm not sure I understood the question because it's a bit of echo. You're asking whether we could use the signal to noise ratio as criterion for
the non-Gaussian noises or not?
No, I don't think we can use I don't see how we could use the signal to noise ratio. In what sense? Maybe if you can elaborate more on what you mean, because what we mean really by signal to noise ratio, I mean, it's
As you have used this to calculate the signal power over the noise power.
yeah, but I mean, what we could use really to check if the noise is Gaussian or not, is simply to take, I guess, a chunk of the time series where we expect there to be no source, which is the case for today's detectors, because there are long chunks of data where there is just silence, just noise, and just study the statistics of the noise of that noise. But I don't think using the signal to noise ratio is doable.
Okay, thank you.
Noise ratio we could define, yeah. Yes, I'm not sure I see how this can be used.
Okay, so naive questions because I did not work with SBIs. So here in these simpler problems, in a sense, you say you do real noise injection. I guess this is because with current data, you have measurement of the noise you have where you do not have the signal. But then in the future, like if I understand correctly, you will always have a signal. You will not have the.
Right. Yeah.
So how is that? I mean, is there a plan, or you just said this is
No,
being
it-
investigated?
I mean, it's no, it's true. For LISA, there will be sources on always, so we'll have to. In fact, the noise itself, when we do this iterative procedure, the level of the noise is a free parameter because it contains all the sources that we still have to extract from the data. So it will be by definition non-Gaussian because the sources are not Gaussian. So yeah, I mean we don't know how to do it.
Okay. So just to make sure, but
Well,
also,
there is I mean I have to say that for LISA there are 3 TDI channels. I don't know if you're familiar with it. There is one channel which at low frequency. I mean, you can take linear combinations of in LISA it's a triangular shaped detector. So it's essentially 3 detectors, 3 Michelson Morley detectors, one of which is degenerate with the others. So, but you can take linear combinations of the output of the detectors, shift them in time, and obtain a channel in which the gravitational wave signal cancels out at low frequency. So that gives you a guidance of what the instrumental noise is. But it's not possible at all frequencies, only at low frequencies.
okay.
But this is why it's challenging to detect, for instance, stochastic backgrounds with this, because you don't know yet.
Good, thank you. And also here, so one thing is this global fit wheel, like that you subtract sort of source by source as you go around, right? And then you look in the rest of the data and dig more, right? But then you mentioned hierarchical something approach, because I was just wondering, is there also approach where you simultaneously fit various sources? Because
Yeah, that I trying to pursue and still doesn't work.
okay, they're too complex.
So, no, it works in certain sense, but I don't know how much people are interested here in the astrophysics. But essentially, I mean, when you have a telescope, and you can think of LISA as a telescope, what you will do is to provide a catalog of sources. In the case of Vera Rubin, you have a catalog of galaxies, and then Emilio will take those galaxies all together and produce a power spectrum and extract the physics. So with LISA, it's the same. We will extract tens of thousands of sources, and then we'll feed them to the astrophysicists, and the astrophysicists will actually do histograms of these sources and extract the slope of the distribution, the normalization, and some hyperparameters. So I was thinking, why not have the middleman and try to extract the hyperparameters of the physical models exactly from data. And theoretically it should work. We have an astrophysical population which depends on some hyperparameters, lambda, number of sources, the sky distribution, the mass function, some PDFs that describe the statistical progress of the population. I can sample those distributions to produce source parameters for each source, masses, spins, and frequency for each source. And then I can produce simulations for the LISA time series or frequency series. And then I can use SBI as a black box to go directly from the time series to the hyperparameters, which are few, without having to extract all the sources. And we tried this in 2Ds for the galactic binary, so for these sources, the white dwarf binaries. So we have 2 hyperparameters. Based on these 2 hyperparameters, which I will not explain, just 2 parameters of the population, we produce millions and millions, 10 to the 7 simulations of this blue population. And we use normalizing flows to infer those 2 hyperparameters. And this is an example in which you see the ground truth is in blue and the posteriors. So we can invert this problem without having to subtract 10,000 or more. In fact, there are many more sources than 10,000. There are many which are below the detection level, which we simulate. And we're trying to scale this up to more dimensions. With more dimensions, it doesn't yet work as well, which is why I said this is preliminary, but in principle, you could do it. I guess the same could be true in other fields. You could use a similar.
Yeah, indeed. No, it's something also I think Christopher similarly does with point sources.
The thing
Yeah,
is, these
it's
things
nice.
are very nice and theoretical, at least for me, and I expect everything should work, and then nothing worked.
Okay, you're preaching to the choir, I guess. Good. Thank you.
More questions? I have one curiosity from the beginning of your talk. If I remember correctly, maybe I'm mistaken, you mentioned that like 4 or 5 neutron stars merger have been detected, but only for one, the 2017, we have the electromagnetic counterpart. Isn't the electromagnetic counterpart the easy part to detect? I mean, naively, this is super naive.
DRB points towards us, yes. If it
That's
doesn't
it.
point towards us, no. There are also, yeah, I mean, there is also one black hole binary in which there's a counterpart, but it's not very 1905, 21. An optical counterpart 2 weeks later. Yeah. The only source for which we have a sound counterpart, which happened within a second from like the merger, is
The 2017, yes.
The others are probably don't have a counterpart because the GRB doesn't point at us, or because the collision angle of the GRB is very small, so very unlikely. This is not what people expect. People expect that we could have many more.
Yeah, I remember that, and the fact that we had a counterpart within a second, it means it had implications on alternative theories of gravity, but
that was a stroke of luck.
Yeah. Okay.
The red sources are the electromagnetic black holes. So these are typically black holes which are in binary systems with a main sequence star. So the main sequence star is tidally disrupted, accretes onto the black hole. The black hole shines in X-rays from the properties of the disk. You can estimate the mass. And this is why people expected that black holes in the LIGO band would have to be in 10 and 20 solar masses at most. But for some reason, the black holes that we see in LIGO are much bigger. Selection bias, which we don't fully understand.
Okay. Okay. We can thank you, Enrico, again. We have lunch downstairs now.